Okay, this is the beginning of the recording. It is Wednesday, April 15th. Good morning. I thought I'd start talking as a bit of a volume check in case you are um, look watching, looking at the recording, watching the recording. I think let's go with watching the recording. So we'll give a couple minutes here. 147 seconds actually. And I've got that on this screen. Let's see if I can pull up this thing, work on this in another tab, maybe. Let's go with yes, hopefully yes. Yeah, I'll have to put this like there, maybe. Why not? Let's try working on this, even if it's 100 seconds. Every minute counts right now. Homework 6. Zoom in on the page, save, and go back to the previous thing. Got 8 seconds. All right. Cool. You're the only one on right now, so without saying names, I'll say I'm glad that a little adjustment will work out for you. All right. Let me get started though here. Um, Usual story, right? So, quizzes Tuesday, Thursday. I feel like all semester long we have never really had a chance to develop too much of a pattern. So, apologies about that. And then, of course, since spring break, things have gotten a little stranger. But just a reminder for those who are either tuned in live or watching this later to please still do the quiz that is due Thursday. And here's the thing, keep current with web work. And let me explain what that means. So I know that one of the frustrations with part of this as a format combined with the topic is sometimes what happens is people start an assignment late, and actually much later than not only than I anticipate, but I think than people themselves do. So I recognize that schedules are a bit strange, but the thing is, if you're starting the assignment that is due this day on this day, then that is actually way too late. Actually, if you go to the syllabus, I did modify the syllabus, of course, based on the week of cancellation that we have, but I didn't actually just push all the deadlines 1 week. What I actually did was I pushed the lecture schedule by 1 week, and I pushed the webwork schedule by a week and then a day. And I know a day doesn't add a lot, but it's meant to create a little bit of a buffer in case people need to, can't attend class live or have some other things going on. I get that a day isn't a lot extra, but the thing is, you start pushing by even more than that. And then, as it is right now, we're looking at with that extra day because of the Monday through Thursday thing, most days of the week, most of our class days of the week, or rather most of our 4 days when a web work assignment is due, there's I think 1 day exception, but now it's a 6 days between when we've talked about a thing in class and then when a web work assignment is due. I start pushing that even one more work day, one more of our class days, and we've got literally a 7 day each time and every time, and that what that does is it creates this there are the pros and cons. So I pushing the 1 day, I hope you understand where I'm coming from with this. What it's trying to create a little bit of a buffer, but you do a little too much of that, and then all of a sudden, we go from we've talked about it in class a week, then literally 7 days ago, a week ago, and then you won't have looked at, if you don't open the assignment at all until the day it's due, then it would be a week later. So people are starting to run into this situation. I am getting people indicating their frustrations um, with how the web work is going, but looking at when people are starting the assignment. Not that I do this very often, but when people say that there's this issue, then I look and I get it. I know there's a lot of things on your plate, and it's easy to just focus on the nearest fire. But I think the thing to do is please keep in mind that as soon as we talk about a topic in class, you should, even if you don't complete that particular web work assignment, you should really start looking at that as soon as possible. Okay. I know that's tough, but the thing is, the more the chain is loosened on this, then it runs into this new problem of we talked about it a week ago. I hope you get what I mean by that. So everything is done with some level of intention here. Nothing, no matter what, somebody's not going to be complete 100% happy with it. But I thought I'd tell you my reasoning behind it. So there is a reason. It's not just how it is for no reason at all. I'd like to start with this optimization problem, and then I think there's a lot of things that appear in this question, so let me take this slow. And I will normally, if this were in class, I would do this question and probably pause and just say something and know that somebody might be confused about a thing, and so I'd try to answer a question. I do know that this format makes it a little harder, so by all means, please ask your questions, but at the same time, I think what I'm going to try to do is, as I talk through, I'll talk as slow as I can, and at the same time, I will try to anticipate the questions, and I'll try to answer them. So it's maybe a little awkward, but I'll do the best I can, given our format. Let me read off the question here. We have a rectangular box with a square base, and this rectangular box is to be made with 5 cardboard sides and a plastic lid. So plastic on top, 5 other sides. Yeah, there's 6 sides total, right? If the box must be 100 cubic centimeters and cardboard is $6 per square centimeter and plastic is $11 per square centimeter, how cheap is the cheapest box? So remember last week with the geometry, this cost issue is actually, I think, the most complicated of the things, so it made sense to save it for the last of our days on optimization, where we could get used to a lot of the other things first. So on the top, if I just shade that right there, that is the part that's made out of plastic, right? So that's going to be the most expensive part, because that part per piece, per square, of the same size per square centimeter, it costs $11, whereas the sides of cardboard are cheaper at $6 per. So there's a lot of things that are going to be going on in this, and I should just comment, we're trying to make this thing cheaply. And maybe $6 per square centimeter and $11 per square centimeter is kind of unrealistic, you might say. But I just wanted to have whole numbers. I get that a more typical story, actually, if you think about this more industrially, would be something like maybe $0.031, for cardboard per square centimeter or something like that. But the numbers get unnecessarily messier to have decimals. So why not just whole numbers, 6, 11, it gets the point across anyway, right? So let's identify the quantities that occur. So I'm just scanning the text here. Square base to be made with 5 cardboard sides. I don't know that really I would say that the number of sides of the box is a quantity. I mean, there's a number attached to it, 5 here, but we know that there's 5 sides around, you know, four around, 1 on bottom, 1 on top. There, you know, a box has 6 sides. What I think of a quantity is more like something you'd assign to a variable where you might not know what number occurs to it, or that variable would appear inside a formula. So take a look right here as we read the next sentence. If the box must be 100 cubic centimeters. So that right there, because it's a cubic centimeters thing, is a volume, right? So that's why there's this quantity of volume mentioned already. And then cardboard is $6 per square centimeter. Plastic is $11 per square centimeter. These are just some cost rates. They will appear in a moment, but they don't represent this C right now. Actually, this C is meant to be the overall cost of making the box. Right? So sorry for not spelling it out as much. I wanted to actually save as much space to work on things here, but this C is meant to represent the cost of a box. And if we're trying to find out how cheap is the cheapest box, we're trying to make this C small, right? And that makes sense that a business would, if they're producing boxes as like, maybe that's not even their main gig. They're making other things. They're making, you know, teddy bears and gift boxes, and then it's the teddy bear that counts, but the box has to be presentable, and so that they have this special plastic lid for some reason. You know, like these things actually could occur for a business, is that as a side project besides their main product, they need to have a certain kind of box, so they want to make that box cheap, of course. And then because the volume formula is going to deal with length, width, and height, these are going to be quantities that we'll just write down right away. So these are the 5 quantities for this problem, and because the question up here says how cheap is the cheapest box, we need to minimize C. Also, it'll be the next slide by the time it occurs, and the question won't be repeated up here, but I'll just comment right now that we eventually need to answer the question of how cheap is the cheapest box. So maybe you know, at least write that down somewhere. You know, how cheap is the cheapest box? We have to answer that question. It's too common. Sometimes people don't answer the question being asked. They do a lot of totally relevant, good math, good work, but you gotta there's a follow through. Make sure to answer the final question. All right. So then the next step after identifying quantities and then identifying which of the quantities is the thing you need to minimize or maximize is to relate the quantities together. So first off, we have a volume formula for boxes we had looked at last week with length times width times height. In addition to this, we can plug in 100. 100, look at the units. The questions tend to be worded this way. They mention something like the number 100 without using the word volume. Like the word volume does not appear in the question up there, in the 3 lines up there. But the fact that it's a cubic centimeters is your cue that this is a volume, right? So this 100 could be plugged in where the V is. So we'll do that. Just replacing the left side where there was a V with a 100, you have 100 is equal to LWH, L times W times H. The other thing we need to do is figure out the cost, and the cost, this is the thing that takes a bit of work, but the thing to remember from last week is the cost is not the same as surface area. You got to understand how surface area is built, and the idea behind cost is like some pieces of surface area cost different amounts than others. So what you have to do is you have to take the area of a certain piece and then multiply by the cost rate. So for instance, the top, right? So if I just temporarily draw a picture of this box again, so the height is, you know, out here somewhere. I'll just draw the hidden parts of the box as well. So length, width. So the top over here, that rectangle has area. So it doesn't involve the h, right? Because the h is that perpendicular, the vertical quantity. But this shaded box, this shaded rectangle on top, it's the same shape as the rectangle on bottom. L times W would be the area. So you take that area, and so that L times W is in units of like square centimeters. And then the thing is, it's that top that lid or the top is made out of plastic, and plastic per square centimeter costs $11. So we take L times W, which represents the area, and multiply by, it's supposed to be $11 per unit of area. So that's why there's here an 11 times LW. I want to pause there, make sure we're doing okay. And maybe I'll just repeat for the sake of it right now that we took the area of the top and you multiply by 11 because it's $11 per square centimeter, and this LW was in square centimeters. So then this, so just to make sure, this LW, the units on LW is square centimeters because it's an area. But when you multiply that by a dollars per square centimeter, right? So you've got this 11, the units on it. Not that I want you to write this in the equation right now, but just to think about this. This is in dollars per square centimeter, whereas the L times W was, that's an area, so it's in square centimeters. So then the square centimeters on top and bottom cancel. And so this entire quantity of 11 times LW is in dollars. So that's the cost of the top. But that's not the only cost. That's why there's a plus, and I wanted to pause here so that we could just think about that part of the cost first. You don't just pay for the top of the box. You also have to pay for the cardboard sides. So it makes sense that we have to add, right? So sometimes people kind of get a little stuck here of like, there's one cost, and in a moment we're going to write down another cost, and what should we do to them? Should we subtract? Should we add? Well, subtract if you didn't have to pay, if somebody was refunding you money. But we have to pay for both of the pieces. And so the other 5 sides, we should look at what's the area of them, but there's another LW here on the bottom. And then notice that there's the front and the back both involve an H, right? The front and the back are an LH and an LH. And then the left and the right side, maybe I'll hatch this way, would be an HW and another HW. So all in all, right here in parentheses, just underlined right now, that is the area of the other 5 sides. So LW for the bottom, as we just said. There's an LH and an LH for the front and back, or the left and right, and then the WH and a WH for the other 2 sides. So underlined there should be the surface area for 5 out of the 6 sides. The 5 sides which need to be made out of cardboard, and so we take that area, and just like we did over here, we took an area. So I've underlined both areas now. I've underlined the LW. We should take an area and multiply by how much money you have to spend per unit of area. So in total, what's written right there is in dollars. What's written right there is in dollars. We got to pay for both of the pieces. So that entire thing, the overall underlined thing, represents the cost. Hope we're doing okay overall. Sometimes people only deal with surface area in this question, but you see how like the surface area is if you add this piece and this piece together. But this question itself does not deal with surface area directly. Pieces of surface area need to be multiplied by the cost rate in order to get the overall cost. Don't do things like set V equal to C. Volume is in cubic centimeters. Cost is in dollars, and so those are different units. Those things should not be set equal to each other. That's sometimes a thing people try to do. The thing is, we need to answer how cheap is the cheapest cost. We've got to minimize C, so we need to solve for C, and we need to differentiate. Look, C is solved for. C is by itself on one side. So we should differentiate this. The problem is we can't yet because there's a total of 3 variables over here. Right? So we should, in the underlined piece, we have to have only one variable, but there's 3 of them. There's L, there's W, there's H. So we should do something about that. One of the nicest, so yeah, if there's a total of 3 variables, we got to get rid of 2 of them. One of the nicest things we can do right away is this square base issue, and we had talked about that last week. If the base is a square, so normally in, well, let me try to draw this so that it doesn't look like a square already. Normally you've got rectangle on bottom, rectangle on top, and L, W, H. So then the fact that you have a square base means these 2 quantities are equal. I've got that on the next slide. So it's square base, so you have L is equal to W. So what you do with that is you get to either replace all your L's with W's or you get to replace all your W's with L's. Your call, either way is right because they're the same. I just happen to not like writing L's too much in my work because they tend to look a little too much like ones. In fact, I had to use a fancy font to make the L kind of a script, kind of loopy look here so it didn't accidentally just look like a one. So what I'm going to do is take this up here. One of the places to replace L with a W is right there. So you have 100 equals, replace this L, and you have W times H. Another way to write that is W squared times H. In addition, we can replace, so not only in this updated volume equation, so we have a new updated volume equation right there, but also right here with the cost, let's also again replace all of the L's with W's. So I hope that looks okay going from here to here. If every L is a W anyway, so 11LW becomes 11WW, or in other words 11W squared. Yeah, and then same deal here, right? LW is WW, in other words W squared, and then this L here got replaced with a W right there. So sorry, that probably looks too messy, so I'll just let you stare at it for a moment. Make sure we're okay. Actually, as long as we're here, the other thing we can do is notice we got a 2WH and a 2WH. You don't have to if you don't want to, but I think it's going to help us out to combine like terms. So this should be a 4WH. And if you distribute 6W squared and then, okay, so I didn't write it out, but it's a 6 times 4WH, so 24WH. Oh, also, if you had 6W squared after distributing, you get to combine that with 11W squared. So I think in the end you'll have C is equal to 17W squared from collecting 11W squared and 6W squared plus 24WH because you do 6 times 4WH. We okay with the algebra there? I did 2 steps in one there. Are we ready to differentiate? Can we differentiate C right now? The story is we cannot yet either, because take a look. This is better. We went from a situation over there where there were 3 variables. Now this is a new way of writing C. These 2 underlying things are equal. They're both C. Of course, I prefer this one because it's shorter, but more important than being shorter, the underlined part over here only has 2 variables, W and H. But there's still 2. The point is there's still 2 variables, right? So I want to differentiate this, but there's still 2 variables. There's W and H. So we got to do something. What are we going to do here? Any takers? Can we take a minute, think about it, share a thought, unmute a mic, type in the chat. The chat box, by the way, is on another screen for me, on my second screen, connect from this, so it will not show up in a recording. But I want you to think about, like, how could we take C, which is written like this, what of the work that we have already was going to be useful in getting from C written this way, where there's both a W and an H, to have only one of those variables? Is there any work from earlier that we discovered but we haven't really done anything with yet that might be helpful? So I would like to really hear from the crowd. It would be good to make sure we're okay. I did get a comment in from the volume thing. Yep. So this here was how we had written the volume earlier. So we took this and then together with L is equal to W, these 2 things combined to give us this, but we didn't really do anything with this 100 equals W squared H yet. Now we should do something with it. So I think we should solve for either W or H, whatever's easier. It's certainly going to be, I think, easier here to solve for H. You could solve for W if you want. Your work would look different than mine. You'd get to the same final answer. It would just be a lot more work. So let's solve for H by dividing both sides by W squared. So 100 over W squared is equal to H. Cool. So now having H is 100 over W squared, we can replace, right? This is a valid way to replace h. So I just copied c. So then there's the 17w squared plus 24w. The h that's at the end right there, I replaced it with 100 over w squared. In addition, I should explain, now that we actually have a way that c is written down using only one variable, just to emphasize that this is a function, I wrote this as c of w. Either of these is correct. I'm not going to, worry about which way you write it with the of w. It's not c times w. I mean like it's c, but now that there's only one variable and I'm trying to think of this like function notation like f of x, this is c of w. Just as a reminder that there's actually only one variable after the equals sign. Yeah, so last week and the week before we were focused on like how do we make f of x larger or largest possible or smallest possible. Now we're asking how do we make c of w largest possible or smallest possible. So think of capital C as like the y and think of little w as like the x, right? Now that we have one variable, we could differentiate this, but I would rather not differentiate this just how it's written because not so good, right? With the multiplication sign, you'd have to use a product rule. With the fraction, you'd have to use a quotient rule, at least as written. So before doing any differentiating, I think it'll help us out if we just clean up a little bit of the algebra here, cancel. So the 17w squared stayed the same, but after canceling a w on top and bottom, there's just a single w in the denominator, so I instead wrote that as w to the negative first. Again, all in the name of just avoiding the quotient rule. Right? So it's convenient to do low algebra first to avoid the quotient rule. Cool. I would suggest that you have at least this way of writing the cost and this way of writing the cost down. Not all this work will appear on the next slide. And now that we have C written in this nice clean format, I would stare at this version of C to get C prime. It'll be super nice, I think. Right? We've done way worse derivative issues before. So C prime or C prime of w, if you wanted to write the of w in, would be 34w minus 2400w to the negative second. Hope that works. The minus sign here is because of the power rule. You got to bring the negative 1 in front and lower negative 1. So negative 1 minus 1, you get to a negative 2. Sometimes people kind of lose train of thought here and accidentally have the exponent to be a 0. So I hope that looks all right. I would like to move to the next slide, but I'll just pause for a moment, see if we're any part of this process so far getting up to the derivative. I will copy the derivative to the top of the next slide, but I just want to make sure we're all okay first. Have any questions of any part? Like any one thing doesn't take a lot of explanation, so don't feel bad asking it. It's just there's a lot of pieces, so I totally get if there's a question or feeling lost or you just want, wait, how did you get from that step to that step again? These are good questions to ask. Question came up. What was the square base step? Yeah. So So the thing is, so being told that we have a square base, normally when you have a box, right, you have an L, W, and an H. And generally speaking, these three variables can all be assigned different numbers, right? Think of like a typical box you get from something in the post office or from Amazon or whatever. Like the box is like, there's three different sides. The length, width, and height are all different. Excuse me. Choking on some coffee here. However, when you're told that you have a square base, that square means that there should be two quantities that are the same. Would we be able to solve it if it wasn't a square base is the question that came up. Yeah, good question. In this particular problem, there's actually literally not enough information given if we were not told that there was a square base. So somehow the problem needed to give, there'd be one too many variables otherwise. So we needed some way to eliminate a variable, and this is a way that it's done, to say that you have a square base. So square base led to L is equal to W. Just other problems, so not this problem, but another way that you might see this is you might not see square base, but you might see problems that say text. Like I think there's a WebWork question out there that says text like if the width is twice the height, language like that. Don't quote me on this right now, but if you see language like if the width is twice the height, then that's telling you width is 2 times the height. So, I mean, there's different versions of this is what I'm saying, right? So this one's not for this question. I'm just trying to think on the spot. So sorry if it's not all that clean. But there, these sorts of problems need to say some other piece of information to help eliminate another variable. So thanks for that question of would we be able to solve it if it wasn't a square base? So I hope I've addressed that, but I still need to go back and still properly address what are we doing with the square base thing anyway, right? So I need to go back to that just to clear up things. So normally these are 3 different variables, but we are given this additional information in this problem that L is equal to W. So that's helpful because this equation right here, which had 3 variables, went down to 2 variables. This cost thing that we had over there that had 3 variables also went down to 2 variables eventually, but still we can't differentiate this yet. I mean, this is what's circled over here for the cost is written correctly. The sad face is because there's still 2 variables, so we can't differentiate it yet. And that means we either need to somehow substitute W or substitute H, one or the other. And that's where these 2 equations, the one that's rectangularly boxed here, and then this circled one, need to play with each other somehow. And because this circled one still has a C variable on the left side and a W and H on the right side, this has a total of 3 variables. It's just 1 variable on the left, 2 variables W and H on the right. So anyway, in any case, we still needed C solved for, so let's not mess with this equation. Let's somehow try to replace either the W's here and here or replace the H there. Whichever is easier to deal with, and which one was easier to deal with, I wouldn't look to this to determine which is easier to deal with. I would just look to this equation boxed here, and it looks like since this equation literally only has 2 variables, like there's not even a variable on the left side, right? It's a number 100. It looks easiest to solve for H, and after solving for H, which we did down here, then we could rewrite this, which we rewrote right over here. The only replacement was made right there, circled. So I hope does that clear up what's going on with the square base? This square base the reasoning, and there is a lot of it, led to L is equal to W, and this L is equal to W, let me just highlight that it applied right there, and it applied right here, right? The fact that L equals W was applied everywhere we could. It's a way to help get rid of a variable. Since there's so many variables, any amount of removing variables that we can is helpful. So what is the cheapest box, or are we not done yet? Yeah, we're not quite done yet, right? So I just want to, yeah, so we computed the derivative. I will comment that when you get to this stage right here, right before differentiating, you're well on your way. Like, we're in a good place. But yeah, we're not done. Yeah, we're not done yet. But I want to make sure that the question that was asked, like, what about that square base step? Are we okay? Can I say anything more? I want to make sure. Yeah, we're definitely not done yet. But I think what's going on right now is we're in a couple different places, which is okay. I just want to make sure that. Okay, cool. All right, so okay, so we have the derivative. I have that at the top of the next slide, right? And now, yeah, so we're not done. What do we do once we have the derivative? Remember, the derivative represents the slope. And the thing is, if we're trying to find either a peak or a valley, if we were to graph it, we're not going to actually graph this thing C. We're not going to graph C by hand. If I just step back a slide, graphing C either in this version or this version, it looks awful. Like this is not something that I expect anybody to graph by hand. But the point of this is, like, even if we did graph it in principle, there should be peaks and valleys, and to find those peaks and valleys, those peaks and valleys occur when the slope is 0. So C prime, the derivative of slope, let's set the slope equal to 0. You'll notice I rewrote the w to the negative second instead as a w to the positive second in the denominator. Again, you see me kind of go back and forth a lot. Like, I often use variable raised to the negative exponent as a format right before I want to differentiate. And then you often will see me push things back into the denominator with a positive exponent if I have an equation, because it's a lot easier for me to think about having actual fractions in an equation, because you can multiply by a denominator on both sides. When I see, of course, you could have written down 34w minus 2400w to the negative second equals 0, like that. This is totally valid, but it's like, then it's hard for me to think of what should I do next in this equation. Kind of written with a fraction, this reminds me, this denominator is a problem, and the nicest way to get rid of having a denominator is to multiply by w squared on both sides. When you multiply by w squared on the left side, you got to distribute your w squared. So you end up with 34w cubed equals 2400. Couple algebra steps here, then we should add 2400 to both sides, then take the new equation, divide both sides by 34, and then to get w by itself, we got to undo the cube, so we need a cube root both sides. You end up with w is equal to the cube root of 2400 over 34. Right? And then you don't need to write this language of is a critical number, like I'm not expecting you to write that on a quiz or test. I'm just using the language here to help remind and connect it back to what we did 2 weeks ago, right? Like that. That's what's going on, right? That's what we were warming up to. This value of w right here, I know it looks awful, but the point is this number is special, right? It does something good. It's either the place where there's a peak or a valley. But which is it? Does this value of w make the value of capital C big, or does it make the value of capital C small? We need to find out. And this is where you need to apply either the first derivative test or the second derivative test. I really, for these sorts of problems, don't really want to do the first derivative test because you need to look at is C prime positive or negative both right before this number and right after this number. And I don't really have much of a clue of what this number is, cube root of 2400 over 34, like what it looks like as a decimal. So I'd rather, it doesn't make sense for me anyway to use the first derivative test here. It would be a lot easier to just take another derivative, and if you look at C prime, it's written two ways, once right here to the left of the equal sign and still up here at the very top line. I think the original way it's written right at the top of the slide. It's a very convenient way to compute C double prime. So 34w differentiates to 34, and then the minus I copied, but then when you differentiate the power rule, the negative 2 comes in front. That's why there's a positive sign there. So yeah, negative 2 times negative 2400 is positive 4800, and then w to the lower the power by 1 to a negative 3. So a little bit of power rule business there. So if all we had to really do was power rule, it's among the things that there are to differentiate. It's not bad. We didn't have to chain rule or anything like that. So this is the second derivative, right? Knowing if the second derivative is plus or minus would let you know if the original C is going to be concave up or down. So let's plug in this special value of w and see if C is going to be concave up or down. So I just took the previous line, everywhere there was a w, so right there and then right there, plugged in this special number w that we had. There are no minus signs here. Sorry for how this is written, but that's an exponent. A negative 3 exponent is really just this base, this quantity written in the denominator with a positive exponent. So all the numbers that you see are positive. If you just take positive things and you add and then multiply, divide, cube root, those kinds of things, you're never going to get a negative number. So you have a positive second derivative. It means that C has a local minimum, right? Because positive second derivative means that the original function, if you were to graph it, should have a local min, because positive second derivative means that if you were to graph C, you would have concave up. And concave up, that cup shape, creates a minimum right at the bottom. Yeah, so this value of w that we had from up here, that's where C is going to have a minimum. That's good. Remember, we wanted the cheapest box. So what we're doing right now is confirming that this value of w is making the cheapest box, not the most expensive box. At this point, we're almost done. Like, we've done a lot of really good math. This is that stage of the problem where I wanted to comment that sometimes what happens is people sort of think they're done and they've just done the math, but you've got to, these are word problems and we've got to make these things useful, meaning we better go back and answer the original question. The original question was, how cheap is a cheapest box? Or worded slightly differently, what is the cost of the cheapest box? Now, is this number right there the cost of the cheapest box? It is not, right? Is this number relevant? Yeah, totally. Right? This number is totally relevant. This value, cube root 2400 over 34, that number is good. It's special. But it's not the cost. It's the value of W that makes the cheapest cost box. So if you want the cheapest box, you better make sure that the width of the box is this number. Right? You got to make sure, yeah, the width of the box has to be cube root of this fraction. But if you say that the cheapest box, oh yeah, cost is in dollars, and you say the cheapest box is this in dollars, that's a problem, because this is a width, so it's in like inches or centimeters. I forget which units that we had in this question, but you see what I mean? Like we need to answer the original question, which was cost, and the thing to do is we know what value of W, this value of W right here, is the thing that makes C small. But what is the value of C? And this is where you need to go back and look amongst all of the things written down from before. And if you know the numerical value of W, we know it's this number, as awful as it looks. If you know the numerical value of W, do you know what the value of C is going to be? And look amongst all your old work, and I promise there's an equation that's helpful. In fact, I did ask you to write down this from the previous slide. So we earlier had that C, whether you write the of W or not, I'm not worried about, but we had that C is this thing. So yeah, if you know what number W is, you can compute what C has to be from that. So I plug this in. All I did literally was take from this line to this line. I just copy pasted and replaced every single, if I did it right, I replaced every W I saw with a cube root of fraction. So then this number right here in dollars, as you see written in words, is the cost of the cheapest box. So that finally answers the question. Like I would say kind of all the work up above the horizontal line I just drew is sometimes a place where people stop. It's like all that work is good, all that work is totally relevant, but you should go back and answer the original question. And after doing all this work, it's so easy to get distracted. Wait, what was the original question again? Right? And so this is why it's important, I think, to answer the original question. It's really important to have a handle of what variable stands for what thing. Okay, now we have reached the end of the question. So there's sort of this last little bit of stuff down here to always do. I'll pause, see if we're doing okay, see if I can address anything. Okay, so I hope, this idea of bringing this thingy back, right? There was this equation where if you knew W, then you could get C. That idea, I forgot about this. Let me say one other thing here. I do have a picture. So I just typed in this C, and so you'll see that right here, this 4.133, so the x-axis represents W here. I just used X's instead of W's because the computer was getting a little confused. So the value of W is 4.133, and then 871, that's on the y-axis. Well, that is C over here. So this point, this y coordinate 871, that's what the cost is. So this 871, that's the decimal form of this number right there. Okay, sorry. Now I got a little distracted. I forgot about that link right there. I just want to talk about bringing up this equation again. So we knew the number that W was, but we needed to know what number C was, and so we brought up this equation that was useful from the past. And I want to make sense of this tip that I included yesterday, but it might have been like, what does this even mean? But the point is, when answering the original question, sorry for the typo in original, you should go back and ask which variable answers the original question. In this case, for instance, in our last example, it's capital C. So then the point is, you probably already solved for that variable. We did, right? So every variable, in fact, back in this problem, we actually have it solved for on one side by itself. If you go back to all there's an L by itself, there's a W by itself, there's an H by itself. Every variable that we have is by itself somewhere. So use that equation, or if you don't want to, you can start over and redo some of the work. But the point is, as soon as you know what number one variable is, you can start plugging that number into some of your other equations. Some take more work than the other. So try to be lazy, find the equation that lets you do the least amount of work to get you to the ultimate value of the variable that you need. Okay, I think one last thing I'll do is right now I'd like to just draw a picture for question 10 together and then give you some moments to try that. So here is from that problem sheet what question 10 says. A new type of gift box is going to be made, an open top box. So this box is missing the top, but it's made by cutting squares from 4 corners of a 12-inch by 12-inch sheet of cardboard. So you start with, let me use a thicker pen here in this app. You start with a 12-inch by 12-inch sheet of cardboard. So I'm going to label, like 12 out here, 12 out there. And then what happens is we're going to be cutting squares out. So the idea is like somewhere right here, a square is just removed, right? So using scissors or something, remove the same shaped square from all of these, right, out from the 4 corners. And then bending up the sides. So if you have this, so the places where I've shaded out, there's no more cardboard there. These squares have been cut out. But then if you bend, that means you can, like, right where the dotted line is, you could kind of bend the cardboard in these spots and then fold these up. So imagine like this those slanted 4-slash pieces right now, that if you bend and then fold them up, so I'm staring down at a tablet right now, like that's literally flat on my table. If those pieces folded up, then this thing becomes a little 3D. Right, so then the question here is, how large should the squares be cut to make the box hold as much as possible? So if you'll notice here, actually, let's just use like the variable c to represent the cut. Here, there, I mean it's everywhere, so let me not label it too many times right now. And you would want to, in this question, think about making the box hold as much as possible. In this question, hold as much as possible is trying to, well, as much as possible, so okay, we're maximizing as part of our objective, but we're maximizing the volume. Right? So I want you to then think about in this box, what's the, I know that volume is normally length times width times height, but I want you to think about what's really the height here. So once you fold up the flaps, it's C. But the real question is, where's the length in the picture? Right? If you fold up right where the dotted lines are, I think you'll see, let me use a new color, that this line segment right there, however long that is, represents the length, and then this line segment here, which happens to be the same length, represents the width, or vice versa. Right? So I want you to stare at the picture for a moment and go like, can we write down how long this blue thing is? It'll involve C, and it'll involve 12 in a certain way. Usually the first guess is that people say L. Well, first of all, L is equal to W in this problem. They're both, you started from a square, and then you chop the same amount out of each corner. But usually what people will say is 12 minus C. It's not quite right. Now, 12 is all the way, 12 is all the way from top to bottom. But you'll notice that this blue segment, if I maybe shift this over to right where this is, you'll see that there's a C right there, but there's another C here. So actually we should update this. It's rather W and L are both 12 minus C, or in other words 12 minus 2C. If you look at the solutions I posted for this specific question, you'll note that I believe I used the method of absolute maxes and mins, which is typically very rare, but the reason I did this is because C is in the following interval. First of all, C could never be negative, right? So the smallest in a sense, in principle, is that C could be 0. And then the largest that C could be, sometimes people want to say 12, but actually the largest that C can be is 6. So why could the largest possible value of C be 6 is as soon as you start cutting the size of this square here, and it grows in size to be 6, then 6 and 6, these should be aligned right next to each other, but I drew a little gap of space between them. Then the squares would completely remove all the cardboard, and anymore, the cuts would overlap, or rather the squares would overlap. So the largest possible value for C would be 6. So it's one of these rare, I mean, you could do the local mins max method, but it's just one sort of rare question where if you notice it, and you don't have to, but if you notice it, because you have a closed bounded interval, you could apply the method of absolute maxes and mins if you'd like. So that option is there. I know we're actually rather short on time, so I will. There's still 7-8 minutes. I would say let me leave this on screen with sort of questions. I can't fit them all on screen, but like 4 through 14 are here. I would ask you to try one of these. Again, these take up some time, but even getting started on any one of these, I think, is a good. These are relevant. These are, I mean, your choices are get stuck. You could leave the conversation and get stuck on your own and then have to join office hours or burn web work points, or you could try these, and when you're stuck, at least you have somebody to talk to about it right here, right now. So maybe pick a question, give it a try, ask a question if you're stuck. Of course, the key is posted, so you could look at that as well. Yeah, sure. So let me go back to right here. So yeah, I guess do you how do you want to do this? So did this make sense? First of all, that the length and the width are both 12 minus 2c. So I mean, if h is c and both L and W are a 12 minus 2c, I think your volume will be length is 12 minus 2c, width is 12 minus 2c, and then h is just a c. And the thing is, we're trying to maximize volume, meaning you need V solved for, check, that's already done, right? So V is L times W times H, and there's L, W, and H. Um, and not only do you need V solved for, which is already done for us, we didn't have to do any algebra to get V by itself on one side, but then you need how it's written on the other side of the equation to only have one variable. That's already set here too. So we can actually, we don't have to do any other substitutions. All the substituting needing to be done is already done. There's only one variable here. I mean, it is written several different places, but there's only one variable. So now it's time to differentiate this. I would not differentiate this just the way it's written. I would prefer actually to, first of all, take this part in the larger set of parentheses here, FOIL that, and then once you FOIL that, distribute the c into it after, and then you'll have this nice polynomial, right? So you'll have like, let's see, let me write that c first. So like 144, what, minus 24c minus 24c, so minus 48c plus 4c squared, and then if you distribute c, a new way of writing v is 144c minus 48c squared plus 4c cubed. So here's a way of writing the volume that only has one variable, and this looks super nice to differentiate. So I think I need to kind of pause here because I've got to clean up my slides, you know, the writing on that for the next section, and stop the recording and all that business, and to restart a new recording.